Welcome, everyone. Good afternoon. It's a pleasure to be here with you today. My name is Karen Benzaev. I'm with the Heinrich-Böll Foundation office in Cape Town, and my role today will be to hold the space for this conversation and try keep it to an hour. We specifically chose to convene this as a meeting, as opposed to convening it as a webinar, because we'd like to, as much as possible, facilitate an open and participatory conversation. But please also note that the meeting is being live streamed. And to those watching on live stream, welcome to you as well. As we start off, please introduce yourself in the chat. And later on, when we open for discussion, we'll encourage you to switch on your camera and microphone if you would like to make contributions and ask questions. Okay. Okay, I see that now we've gained more participants, so that's good. Let's continue. So by way of introduction to the topic, over the past few years, we've been hearing a lot about green hydrogen and the role that it could play in mitigating climate change. To those who are not familiar, what is often called green hydrogen is hydrogen made using renewable energy. This is different to gray, black, or brown hydrogen, which refers to hydrogen made using coal or gas. There are a number of important economic sectors that currently depend on gray, brown, or black hydrogen. So the conversation about green hydrogen and climate change has focused on whether green hydrogen could decarbonize these so-called hard-to-abate sectors. It has been a rather controversial conversation, with some convinced that green hydrogen is absolutely essential to our abilities to tackle climate change, and that it could actually form a backbone for green industrialization in lower income economies, while others have expressed a great deal of skepticism. There are many questions regarding whether green hydrogen could be a socially and environmentally desirable solution, and whether it's even economically viable. So it is in this context that we've also started hearing more about a new hydrogen color, this time white hydrogen. This refers to a hydrogen that is formed through geological processes deep below the surface of the Earth, and therefore is called sometimes natural hydrogen. We'll be using the term geogenic hydrogen because increasingly the color-based labeling system is becoming meaningless, with new colors regularly being made up, sometimes as parts of all sorts of campaigns. Given how much conversation we've had on green hydrogen, how much research we've seen on it, there's been a notable absence of conversation about geogenic hydrogen. And this is something that, as the foundation, we wanted to address. And so we're really pleased to today launch a policy paper on the subject, and to do so in the company of 3 experts who will share with us findings from their recent research. First, Dr. Kramer, the author of our policy brief, will introduce us to what geogenic hydrogen actually is and give us a global overview of where it is being pursued and what role, if any, it could play in the energy transition and what this would entail. We will then zoom into questions of geogenic hydrogen a little bit closer to home, for me at least, with research looking into it in Mpumalanga. This is research that has been undertaken by Professor Bambi and Dr. Smith. So I'm aware that conversations about hydrogen can be quite inaccessible. They're full of jargon and technical concepts. And while the policy brief we're launching introduces geogenic hydrogen, we will also post a resource in the chat that introduces green or renewable hydrogen in an accessible way. So please refer to that if needed. In addition, after each of the presentations, and before we open for discussion, I will provide time for questions of clarity so that we can all stay on the same page. At the same time, I'd also like to propose that we don't get too bogged down by the technical specifics, because the social, economic, and ecological questions relating to geogenic hydrogen and its role in the energy transition are as important, if not more, than the technical questions. And so, without further ado, let me introduce our esteemed guests. Our first speaker, Dr. Stefan Kramer, who is the author of our policy brief, has a PhD in sedimentology and groundwater chemistry from the Free University of Berlin. He was formerly the head of the Africa department of the Heinrich-Böll Foundation and the director of its regional office for Southern Africa in Johannesburg. Following his time in Johannesburg, Dr. Kramer led the Heinrich-Böll office for Western Africa in Lagos. He's now retired, but takes on regular university assignments, most recently in Bolivia. Our second presentation will be by Professor Bambi, who is Professor of Geology at the University of Pretoria. His research has focused on sedimentary basins and the geological history of the continent. He's currently involved in a multi-country research looking at geogenic hydrogen in South Africa, Mozambique, Morocco, and Togo, and whether these sources could benefit local communities. Dr. Ansie Smith is also with the University of Pretoria and has a PhD in financial mathematics and mathematical statistics. She's applied these skills in hazard and risk assessment, especially in the earth sciences sector. Her current focus includes statistical and geostatistical modeling to track the occurrences of white hydrogen in Mpumalanga, about which you will hear more today. She will join us for the Q&A part of this meeting, owing to travel and connectivity issues. And with that, let me hand over to Dr. Kramer and ask him to start the first presentation.
Okay, thank you very much, Karen, for this kind introduction. I still very much remember maybe some 20 years ago when I was head of the Heinrich-Böll Foundation and hired you, and I'm very happy to see that you have really made a career within Heinrich-Böll Foundation. It's good to see you here again. Let me just start my little presentation. Okay, can you hear? Yes, I think you can hear me and you can see my presentation. I'm going to talk about geogenic hydrogen, whether it's a phantasma or a game changer. That's what you basically mentioned in your introduction. And I was very happy that Heinrich Böll asked me to do a little bit of research. Most of my research dates from last year, from the summer of last year, and a little bit of updates. So I'm very much interested also to hear what Professor Bambi is telling me about other projects in Africa, because it's a fast-moving field. In a summary, please accept that I think hydrogen is the most important carbon-free fuel that can help us into a carbon-free, zero-carbon future. As a particularly in transportation and in other hard areas. But it's quite clear to me that all known resources and research and procedures to produce hydrogen for 100% replacement of all fossil fuels is virtually impossible at this point in time for technical reasons. White hydrogen or geogenic hydrogen is actually available in quantities exceeding future demand predictions. That's a big word, and that's basically my point I'm going to show. But the lack of research and exploration at this time means it will be too little and too late for having a serious impact on our fight against harmful climate change. You asked me to do a little review of the color coding terminology, and there is quite an accepted terminology, but it's, as you said, mentioned it's fast-moving green hydrogen is the one produced from renewable energy, and the main process is electrolysis. The same is with solar or grid electricity. That is called yellow, sometimes also from pink. Pink hydrogen is the one made by electrolysis from nuclear energy. Blue, turquoise, and gray hydrogen are all made from natural gas by different technical processes and differentiating whether there's carbon capture and sequestration or not. and brown or black sometimes hydrogen is from coal and from biomass by gasification. So in this terminology, white hydrogen is not yet there, and white hydrogen is coming out of a hole like this. That is one of the more famous geysers in Iceland, and their hydrogen content is substantial. So with every explosion or every eruption of a geyser, there's quite a number of kilograms of hydrogen vented into the atmosphere. There are very historic sites like Chimera Mountains in Turkey, where gas has come out for 2,500 years, at least it is recorded, and has a high percentage of hydrogen in it. And we have the famous fairy circles in Namibia, where they were first described and discovered with circles of sometimes 10 with up to 100 meters diameter, where there are virtually no plants growing. And the original idea was that fairies are dancing there. That's why the plants cannot grow. We find that most of these are hydrogen seeps, and we find them all across the world. Real hydrogen production was first observed in the mid-Atlantic Ocean ridge in the place called Lost City by an American research crew, where through geological processes, um, seawater is interacting in seeps and in the deep soil with hydrothermal systems, which then produce hydrogen. And it's serpentinization really at the surface and sometimes deeper in the ground. Serpentinization is the main process of how natural or geologic or geogenic hydrogen is actually produced, and it's produced wherever heat is produced in the earth, especially when different layers of rocks are moving against each other in all kinds of tectonic settings. The friction along these plate boundaries creates heat, and this heat produces the oxidation of iron minerals, which then releases hydrogen. That is the most important process, where there are about 30 other processes, but quantity-wise, this is the most important process, and the oxidization of the minerals then leads to release of hydrogen. That is the main process. And the chemical process, I'll just give you a quick rundown here, is iron and manganese silicates like olivine, which is the most abundant mineral in the upper mantle, is then added with seawater or groundwater and forms another mineral, which is called serpentine, which is magnesium silicate and magnetite, plus hydrogen oxide, that is then released. This is the whole process of geological formation, or one of the most important processes of geological transformation of olivine to serpentine, and that is happening everywhere in the world and continuously. So in this case, geogenic hydrogen could be even seen as a renewable resource because it is continuously produced. It has been first discovered in some odd places, for example, in a chromite mine in Albania, which had some unexplained underground explosions, because they found that in the mine water in the mine there is a high percentage of hydrogen, and this seemed to be the first system of hydrogen production which has been studied deep underground. The other famous example is in the Burakay Bugu in Mali, where when they drilled for groundwater, they hit an hydrogen bubble, and the whole borehole exploded. Until today, it is a 20 years of continuous production of hydrogen in Burakebugu, north of Bamako, supplying electricity to a local village. Still small scale, but for 20 years of continuous production raises a number of very interesting geological questions, which we are not going to do today. This is a map of African projects where we have seen some research or some indications of hydrogen, and many more are discovered as we are looking closer. The whole point of this slide here is to show that it is quite a widespread resource all across the continent and many other continents, because the processes which are currently known for hydrogen production are virtually ubiquitous in many places. There is the serpentinization, which I mentioned earlier ago, and the radiolysis is the second important process where radioactive minerals lead to the dissociation of the water molecules, and hydrogen is produced. Deep sea hydrogen is kind of a degassing of deep-seated magmas. Thermogenesis is a process where tectonic energy releases hydrogen along fracture zones, and oxidization is a process of ophiolite intrusions where seawater or groundwater is interacting with these rocks and leading to hydrogen formation. A very famous example, which is currently studied in detail, is the ophiolites in Oman, which can be even stimulated, like as we did it as we know it from natural gas. The introduction or the injection of water into these highly reactive oxidization zones of ophiolites can actually stimulate the process of hydrogen production. And microbial decomposition especially from coal deposits, but also from gas and oil deposits, can lead to hydrogen seeps. And maybe we'll hear more about that in the South African example. It is a widespread resource known in particular in France. If we look at the European scale, France has some of the highest amount of hydrogen deposits in the Lorraine area, very well studied in the meantime, and France is the only European country which has already introduced particular legislation to facilitate exploration and production of hydrogen. Turkey has examples in Albania, in Spain, in other France localities. Italy has in the Alps something, in Romania, in Poland. So it is a widespread resource, not only in Europe and in Africa. The big problem is actually the pipelines which would be used for these, because hydrogen pipelines are separate from natural gas pipelines and need to be refitted, and this is a very expensive process. Otherwise, many of the infrastructure of the gas industry could be used for hydrogen production. The US is probably most advanced in having already dedicated drill sites for hydrogen deposits, particularly in Nebraska and in Kansas. Hydrogen is probably produced in all the black late areas of Precambrian domains and across the world. And okay, somebody has music on. The research into hydrogen is still very sketchy, I would say. The US is probably leading it, with the US Geological Survey being the most active institution in this regard. France is probably second, and all the blue-colored countries here have research programs of one type, of another. But overall, it's still very much an infant science, has been neglected for a number of technical and scientific reasons. The US has already produced a prospectivity map of geologic hydrogen, and the darker the colors, the higher the prospectivity of geological formations in the US, and it's particularly in the Great Lakes areas and in the northern plains, in the western plains, so, based on US Geological Survey. One of the reasons why geologic hydrogen could be a very important game changer is the price tag, because currently hydrogen produced from methane is $2 to $3 per kilogram of H2. From methane with carbon capture, it's a bit higher. Coal is probably the cheapest. Renewable energy is up to €8 US dollars per kilogram of H2. And nuclear is slightly cheaper, but still very expensive. And all the calculations so far of geogenic or white hydrogen are up to $1 of a kilogram. That is kind of a game changer if it ever can come on stream. We'll hear about it in Mpumalanga for a little bit later. And the latest research is from December 2024, again from Jeffrey Ellis from the US Geological Survey. And they just, in the Science Advances, published a paper a few weeks ago. And they have produced the first mass balance model for geogenic hydrogen. How much is it actually produced, and how much could be found? Sorry, and it's about 100,000 million tons of hydrogen per year, which is 2% of the global production of hydrogen in the subsoil. That would be equivalent to 200 years of energy consumption at the time when it would be actually produced. That gives you an idea of the quantities involved in hydrogen production. But the big problem is actually it's not yet there, and to produce and to create a whole industry with exploration, drilling, with the infrastructure, and with cost competitive, and comparing it with cost competitive water electrolysis will take 20 to 30 years, judging from how fast technology can be developed, how fast legal processes can take, how fast companies can invest. And by 20 to 30 years, we are close to the year 2050. And by that time, water electrolysis from other sources may be even more cost competitive. That is the big gamble. And that is why I believe that geogenic hydrogen is a wonderful resource, so very plentiful, renewable, but it is too little, too late. There are a number of projects at present who are operating across the world, but this slide actually hides the fact that there are far too little projects, and none of the big boys in the industry, big oil and gas industries, are notably absent from this world at present. So it's more research by either startup companies or by universities, like we will have here a little bit later. All the other details can be seen in my paper here. And that's why I think geogenic hydrogen is a wonderful stuff, but it's too little and too late. Thank you very much.
Thank you so much, Stefan, for this really informative presentation. Before we hand over to Professor Bambi, I wonder if I can just check if there are any questions of clarification that any of the participants would like to pose now. If you do, please put up your hand, put it in the chat. Going, gone. If you have any, you can hold them over for the question round after Professor Bambi. So let me please invite Professor Bambi onto the stage for as I said, a look that's closer to home for me, looking at white hydrogen in Mpumalanga.
Thanks, everyone. Thank you very much for the brilliant introduction, very comprehensive. Thank you, Dr. Kramer. So I'm just going to start sharing now. Don't seem to be doing much sharing at the moment.
I can see your presentation.
Really? Okay. Well, it's just me
Yeah.
that can't see my own. I'll look on my other screen then. Okay, let's go from the beginning. Okay, we are in presentation mode now, I think. Let me just get a pointer. There we go. Thanks very much. So, as Dr. Crom has indicated, to make a start in Southern Africa, myself and Nancy Smith have been leading a project here from the University of Pretoria to look in Mpumalanga province in South Africa. Thanks. We are a fairly small part of a major, well, a much larger group known as High Africa. This is falling under the banner of an acronym called LEAP-RE, which is Long-Term Joint European Union African Union Research and Innovation Partnership on Renewable Energy. So we have consortium partners in Portugal, Converge, and in Germany, Liège and Fraunhofer. Here in South Africa, we're sponsored by an organization called SANEDI. The acronym there stands for the South African National Energy Development Institute. So that's who's funding us. Just in case your geography of South Africa is not so good, I've just circled there Mpumalanga. It's the province just to the east of where we are here in Pretoria. That's Gauteng. And so we're bordering up on the Eswatini border. Just on the right-hand side there, you can see a geological map. Similarly, our study area is circled there. Geologically, it's in quite an interesting place for the geoscientists amongst you. We're located on these relatively young rocks from the Karoo supergroup, but we're very close to the boundary of all of these other rocks up to the north. And these are all much, much older. They're Precambrian in age. And we'll obviously get back to this when I start talking about the geology. But that, I think, is quite an important geological factor for what's going on. So we will get back to the geology later on. So what drew us to Mpumalanga in particular were these rather striking looking subcircular depressions that you can see here. In different parts of the world, they're called different things. We've heard about fairy circles from Dr. Kramer. In the US, they call them Carolina Bays, subcircular depressions, they're sometimes known as. Here in South Africa, we call them pans. And the obvious attraction of these pans here in Mpumalanga province are that they look remarkably like known hydrogen, natural hydrogen, geogenic hydrogen occurrences here in South Carolina. These are the so-called Carolina Bays, as they call them. You can see these exact same depressions. This is a LiDAR image just to pick them out a bit better because it is quite well vegetated. And notice that they are sort of oval in shape. They're elliptical. And the long axis of all of those ellipses there in South Carolina all line up. And we have exactly the same thing here in Mpumalanga. You can see that these pans are elliptical. And if you look at those long axes of all the ellipses, almost exactly the same. Maybe not quite as dense as the Carolina ones, but nevertheless, we've got about, well, nearly 5,000 of these are present in Mpumalanga, and the vast majority of them are all conforming to this strange elliptical preferred orientation. So obviously people have known about these pans for many years, and the previous thinking before we came along and changed things was that this was due to drainage derangement. So the idea was that all of these pans were once connected by rivers, and the rivers have stopped flowing because of tectonic uplift, stopping the flow of water in a particular direction, and left these pans behind. We now think that's nonsense because we went along with our hydrogen measuring equipment, and we found, as I'll show you shortly, we found significant amounts of hydrogen. We're doing pretty basic, cheap science here. This is the equipment that we're using, and we've borrowed it from various other industries. We've got an ordinary drill that a construction worker might use, battery powered, so we can use it in the field. And we connect that to a drill bit that's about 1 meter long and about 14, 15 millimeters in diameter. And that allows us to drill approximately a meter deep hole into the soil. And into that hole, the second that we've drilled it, we extract the drill bit and shove in a hydrogen probe. You can see the stick probe here, and there it is in action over on the right-hand side. We've put it into the hole very quickly. There's a tube coming out of the top, and that runs through to this little machine, also shown here on the left-hand side. And that's a hydrogen probe that we're using, and it's from the industrial plumbing industry. They use them for leak detection. The idea is if you've got a leaky buried pipeline, you pump hydrogen in from bottles and you go along with these probes, and where you have a big showing of hydrogen coming out of the pipe, that's where your leak is. So we're just repurposing industrial equipment. Also, you can get gas probes from the landfill site, gas monitoring industry, that measure a variety of different gases, hydrogen included. So again, they can just be repurposed and used for these measurements. So when we take this equipment into this Mpumalanga pan field, we notice a couple of things. Firstly, if you just go along the roads, just for ease of access, we did surveys along these roads at regular intervals, and you'll notice on this little graphic that that there are these little diamond shapes, and that's scaled according to the bin into which of hydrogen concentration. So these little small symbols, like you see here, that means hardly anything was found. And you'll see down here a whole suite of much bigger ones. You'll notice we got very excited about this area. So if you're away from the pans, the background hydrogen level when we drill these holes and put in the probe, it's about 2.5 part per million or less of hydrogen. In the atmosphere, it's about 0.5 part per million, so it's only slightly elevated above that and really not of great interest. But as you get to a pan, there's a pan hiding under all of those results, and we can see another pan up there, and notice that these diamond shapes get considerably larger. And it's not uncommon for us to get several hundred ppm, on some occasions several thousand ppm, and in one part of the study area, we've got up to 45,000 ppm. That's 4.5%. Hydrogen will burn in the atmosphere at 4%. So potentially, even though we're only sniffing around at the surface with our meter-deep boreholes, we've discovered hydrogen that might well be combustible. So we think that's quite exciting, and it's certainly indicative that there's something going on at depth. Just zoom in on those. That's that same pan that we saw before. So you can see we've been all the way around the edge of it, taking hydrogen measurements with not uncommon results of between 200 and 1000 ppm. All of these larger diamond shapes that you see are where we recorded those pretty significant elevations above that 2.5 ppm background levels. Jumping just to another location elsewhere within the field area. This is a little bit further out to the east, closer to the Swazi border. And that big location there, we've been back there time and time again, and this is where we got 4.5%. And we've frequently had measurements in that highly elevated manner. So we're pretty sure there's something going on. As geologists, Nancy Smith and I are interested in why there should be hydrogen. And that's where we start to get a little bit confused. If we take these pans as being the sites of elevated hydrogen, what we did is plotted the pans, overlaying it with some of the geology. And you can notice from this figure here that there's a very close coincidence between the pans, which are these blue-black dots. It's obviously quite a small-scale map, sorry, large-scale map. But notice that all of them, pretty much, with a few exceptions, but all of them are located on this pink rock. And this is the Permian-aged Eka group. Ironically enough, this is the same rock in which South Africa's coal is preserved. And so this whole area is riddled with coal mines producing South Africa's electricity by coal. So it seems to be a multi-purpose rock. It's delivering us fossil fuels, and maybe it's delivering us suitable amounts of natural geogenic hydrogen as well. As soon as you get off those Permian-aged rocks onto the younger rocks that I highlighted a little bit earlier in my talk, into these greenish colored ones, then suddenly the pans stop, and so presumably those leaks of hydrogen is stopping as well. Just in a little bit more detail, this the pink rock that you see on this map, it's this sort of brownish and in some areas a grayish colored rock. You can quite clearly see the boundary between the younger Permian rocks and the older Precambrian rocks, and I've added little red dots on here for the pans, and you can see how coincident they really are. So it's interesting.
Professor Dunby, if I could just give you a couple of minutes to wrap up, please.
Super, thanks, Karen. So it would be tempting to think that the hydrogen is coming from these Permian-aged rocks, but as Dr. Kramer showed, you really need deep level activities. Serpentinization is taking place about 4 to 10 kilometers down. That's where you need enough heat at that depth to drive these serpentinization reactions. I'm just going to shoot forward a bit. Another interesting coincidence is that long axis of these pans that we've highlighted before is parallel to faults. So faults are probably acting as sources where the hydrogen can leak up to the surface. Zoom straight on. In terms of what the sources might be, again, each of these dots that you see here, those are the pans, and notice that many of them are over this huge gravity anomaly. This is the Bushveld complex, which are mafic rocks, about 11-kilometer thick sequence of mafic rocks, potentially getting to a suitable depth that they might be undergoing serpentinization. But there are also these areas out in the east and this area in the west, well away from those Bushveld complex rocks. So the Bushveld complex can't account for hydrogen occurrences over here in the far southeast or the far southwest. So there may be other sources of hydrogen as well. Again, our study area is in this oval shape, and notice that just up to the northeast of our study area, we have an Archean-aged greenstone belt that probably continues at depth under here. Greenstone belts are ultramafic rocks. They're prone to serpentinization. We also have the Transvaal supergroup running down here. That's full of ironstones, which can potentially produce hydrogen. And we've got Archean-aged granitoids, which are likely to be radioactive, buried underneath these coal-bearing rocks, and perhaps undergoing radiolysis, producing hydrogen by that method. So this next image that Dr. Kramer also showed, it's a hydrogen system. It's got all of the factors in there that might affect whether we have a suitable hydrogen factory or not. And we've got many things in this image here in Mpumalanga. We've got the basement rocks with granites that could produce hydrogen by radiolysis. We've got olivine and pyroxene bearing mafic and ultramafic rocks in abundance that could be undergoing serpentinization. We've got those younger coal-bearing rocks that might be acting as a trap, and we've got the little faults that might be allowing it up to the surface, and that's where we measure it parallel with the faults along those pans. So that's my conclusion. It's likely that the pans are linked to the flux of geogenic hydrogen from deep level out into the atmosphere. It's likely that that hydrogen is linked to the presence of iron-rich minerals in mafic and ultramafic rocks at depth, which are undergoing serpentinization, or maybe it's radiolysis in the granites. All of it is there. We're not sure which might be the source. Maybe we've got multiple sources. The Ecker group rocks at the surface, we think that they might be acting as the trap, stopping the hydrogen coming up to the surface unless they're broken up by faults, in which case the hydrogen seeps up, and that's where we get a pan. Okay. So we're at an early stage. As Dr. Kramer highlighted, the whole industry of geogenic hydrogen is in its infancy, and it's very much the case with us. We haven't drilled down more than a meter. So we're at a very early stage in exploration. We've really no certainty regarding how exploitable or scalable the hydrogen might be to make it an industrial scale possibility. Our original concept for this project was that we might be able to produce enough hydrogen for small scale standalone generation units like the ones that we see in Barakabogum that Dr. Kramer illustrated. So it's yet to be seen exactly what is down there, but fingers crossed within the coming years there may be something that's utilizable in these hydrogen occurrences that we have. Just a couple of references that I've used.
That's really brilliant. Thank you so much, Professor Bambi.
Thank you.
Must admit, as a non-geologist, I'm feeling a little bit left out. As another side note, what I should probably add is that Mpumalanga is really the heart of South Africa's energy transition. As Professor Bambi mentioned, it is the location of, I think, about 80% of South Africa's coal. And I would say all of its most important coal-fired power stations, with the exception of one. So I think the question of what is next is a particularly relevant question here, particularly from a social justice perspective. We've had one question thus far in the chat, and that was from Maximilian Rischer. Hope I'm pronouncing that correctly. Maximilian, I wonder if you want to come in and ask your question. And others, please feel free to come in at this point and ask questions.
Not sure he's still in the call, but his colleague is, so.
Oh, I see. Sorry. Well, Maximilian, perhaps he posted this on the chat because he was leaving, asked whether there are any major technological hurdles to sourcing the hydrogen today, which I think really speaks to the question of what is next, and gets to the heart of it. I don't know, Professor Bambi or Dr. Smith or Dr. Kramer, whether you'd like to come in on that. And then I note that David Walwyn would like to come in and ask a question.
I can say a few words about the technological hurdles because I've looked at it at some stage. Hydrogen is a really tricky stuff. It's highly explosive and it seeps through all kinds of steel and joints and so on. It requires a very different protocol of safety, of transportation, of refrigeration to ship it by containers or so. So it's a very tricky stuff. Secondly, it is usually found in places where there is no infrastructure, where there is no previous gas and oil industry, because its generation is different, except probably from the places where it's generated from coal and gas. And thirdly, it is often not a pure gas. It is not just only hydrogen. It is always contaminated with quite a number of other gases, some of them toxic like H2S, some of them useless like CO2, some of them are beneficial like helium or like natural gas. And so there is a need for technical separation. And that is dependent on the continuity, and hydrogen seeps, as far as they have studied so far, are quite changeable. They change in composition and in quantities over time, and that makes industrial production not easy because you are dealing with a changing product. So this is from a purely technological or geological point of view.
Thanks, Dr. Kramer. I wonder, Professor Bambi, do you want to also come in on this? Given that in our earlier conversation and in your last comment, you mentioned the interest around whether this could actually be a resource for communities in Mpumalanga.
Yeah, that was our original idea, that rather than being a very large scale hydrogen production, industrial scale development, that this, to get around the problems of transportation that Dr. Kramer has just discussed, that we use it in situ. The images that Dr. Kramer showed in his presentation of the Barakabogo occurrence, obviously very, very small scale. There's a little holding tank, I understand, and that's just fed into a car engine, which runs a little generator, and a village has cheap, free, renewable, carbon-friendly energy. So that was the sort of small-scale use of any hydrogen that we envisaged. Within that part of Mpumalanga, it's, as you highlighted, it's the area where they produce the nation's electricity, and there's quite a big population, but they already have electricity. They're already hooked up to the national grids, unlike Barakabogo, which I think probably wasn't prior to the installation of that infrastructure. So yeah, certainly in South Africa, one of the issues is that if we're right, if there is a usable supply of hydrogen, they don't really need it for electricity. We've had some electricity interruptions in the country, but that seems to have been solved now. But maybe I can look at this from another point about where to drill for hydrogen. And maybe I sort of created the impression with those little colored diamonds on my maps that that's where all the hydrogen is. That's where it's leaking. So my feeling is probably between the pans might be the best place to drill, because that's where it's not leaking. If there's no pan, there's no leak. But this is a guess. Nobody has drilled, least of all us, to anywhere beyond a meter depth. Barakabogo, they went down 100 meters. They were actually drilling a water borehole and found it by accident. So yeah, I think we need the next step would be a drilling campaign to go through the trap rocks to see what's there at depth below that.
Thanks so much. David, I'd like to give you the floor. If perhaps you can introduce yourself, and I understand that you have a question regarding the levelized cost of hydrogen.
Okay, just let me check. You can see me, you can hear me.
I can hear you. Now I can see
brilliant.
you. Welcome.
Okay, there we go. Yeah, I mean, first of all, greetings to everyone, but especially greetings to Stefan. Stefan, I had no idea that you were involved in this area. I only know, Stefan and I know each other from Johannesburg many years ago, where Stefan was working on another geogenic resource, which was natural, well, gas and fracking of gas from the Karoo Basin. So good to see you and to read your report. Thank you very much for that and your presentation. I'm also working on this. I'm a colleague of Professor Bambi, also at the University of Pretoria. I'm a professor in the graduate, or emeritus in the Graduate School of Technology Management. And I'm working on this project together with Adam. I'm doing basically one of the work packages, which is a combination of techno-economics and socioeconomics. So I'm interested in the socioeconomic impact of white hydrogen or geogenic hydrogen in the Mpumalanga region. And I'm not doing the techno-economics that's been done by the Fraunhofer Institute. And they are struggling with this. So we've reached a bit of an impasse, actually, because you can't do a socioeconomic assessment or an impact assessment unless you can say, this is the size of the resource and this is what its cost is going to be, and this is the kind of benefit that might accrue as a consequence of the utilization of this resource. So we aren't anywhere near where we can do a sensible socioeconomic impact study. But I wanted to ask Stefan about this question of the LCOH, the levelized cost of hydrogen. I'm sure everyone who's attending this knows what that term is. And Stefan gave a value which is for natural hydrogen about $1 a kilogram. Now, I've looked for values for the LCOH for natural hydrogen. I cannot find anything sensible. No one, it seems to me, has done any study. No one's published any results. So even that value of $1 a kilogram just seems to me fictitious. It's like pie in the sky. It could be $6, it could be $600 a kilogram. And if if, for instance, if you're extracting hydrogen at, let's say, less than 0.5%, and you have to do the purification and then you have to do a concentration and then convert it into some form of usable energy, you're just never going to get to $1 a kilogram. So in any case, Stefan, please, do you have any information on LCOH? Won't you share that with us or maybe send it to me? I'd love to see it.
Well, you hit a soft spot, I must say, I must admit, and good to see you again, David. Yeah, I'm just quoting industry sources. It's just what American companies have calculated from their data of sources, cost of drilling, cost of production. They're in an American context where there is a dense network of pipelines, which lowers the cost substantially, where there is an industry which is ready to go, whether there's technology available. It depends very much on all these factors. And it is the only available published figure which is from industry sources. And I must admit, and I agree with you, that it is not 100% reliable or believable. There is no practical case study where this could have been shown so far. It is still early days.
Thanks, Stefan. I mean, I think this is an area in which there is so much speculation and guessing. I think we've been talking for a while about the green hydrogen hype, but when I was reading your paper, I really was thinking about the term white magic as perhaps a corollary. I have a question regarding the volatility of hydrogen, both from a safety perspective, both to humans, but also an ecological safety perspective. So I think we all know hydrogen is an extremely volatile molecule. Professor Bambi just mentioned that. And from a human perspective, from a human safety perspective, I'd be interested in how safety has been managed within the context of the village in Mali. But I think there's also a question around ecological safety from a white hydrogen perspective. And again, Professor Bambi, you mentioned the issue of hydrogen leakage. And that was something that Professor Kramer, or Dr. Kramer, also mentioned in his research. Hydrogen is not a greenhouse gas, but it does have a greenhouse effect. So it increases the longevity of methane and other greenhouse gases in the atmosphere. So although it's not a greenhouse gas, it does have a negative impact on climate change. How do we factor these two safety questions into our assessment of whether this should be pursued or not?
Well, let me start, and then you, Adam, you come in. I agree with you. It's really a tricky substance, and its leakage is difficult to control. The industry has already protocols in place how to operate hydrogen pipelines because it's been using it for some time. So I think technologically it can be managed, but you are asking for environmental impact and social impact of hydrogen, of drilling for, let's say, of massive drilling for hydrogen in many places. The fact is that currently hydrogen is leaking in a massive scale, completely unnoticed because we have never looked at it. But just like the Mpumalanga example shows that there is lots of spaces around the world where hydrogen seeps out unchecked and uncontrolled. So one could even argue, if we are managing to even capture a fraction of that, that would reduce the footprint of hydrogen emanations into the environment and would put it to a good use. At least in that sense, it may offset the kind of additional leakages which may come from extended drilling campaigns. That is a guess, but it's not been proven because we know so little. And in the Mpumalanga case study, it shows composition of soil gases, but not fluxes. We don't know how much of that is actually escaping to the environment. There are some examples from Brazil where it has been studied already. And from there, we know fluxes are quite substantial, but very different even from day to night and from winter to summer. There seem to be a couple of poorly understood processes at place.
Thank you. Yeah, Professor Bambi.
A couple of things to add into that. Yeah, Dr. Kramer was speaking just now about the rate at which hydrogen leaks, and we've been putting in quite a bit of effort trying to figure out the rate at which hydrogen comes out. What we found is if we go to one of these pans and measure, and we come back the next day to try and get another high measurement, and there's nothing. And this is quite similar to the Brazilian case, where more work has been done with in situ constant monitoring, and they've uncovered a certain periodicity in the rate at which hydrogen comes out. What the Brazilian case shows is that during the day it's high, and then at night time it drops down. So we went out to try and see if we could see something similar. We dispatched students on 3-hour regular overnight expeditions to go and measure. They were a bit upset with us because it's cold up in that part of Mpumalanga, but we could find no patterns to the rate at which hydrogen comes out of the ground. We even went at full moon, new moon, and half moon to try and see if there was an earth tide effect on hydrogen. Nothing, almost. So the conclusion we've come to is that this hydrogen is coming out both spatially and temporally in these sort of hydrogen burps out of the ground. They come up to the surface and then it all goes away. And it's almost random where and when the next emission of hydrogen will come, unlike in Brazil, where they seem to have a much more rigorous periodicity to the hydrogen emissions. So very, very difficult to quantify how much hydrogen is being lost out into the atmosphere and then out into space. The other thing I wanted to talk about it with regards to the environmental impact of burning hydrogen, I think it depends how you use it. In Barakabogu, as I mentioned, they're just burning it in a car engine. It's, I think, a Ford V8, for those of you that are into engines, and they just instead of putting in a mixture of fuel and air, they put in a mixture of hydrogen and air, and it burns away. If you're burning it in a car engine, I'm way out of my field of expertise here, but I understand that although there's no carbon dioxide produced as a result of that combustion, there are a suite of nitrogen oxides that are produced, which are also fairly nasty chemicals. Using the hydrogen in fuel cells, on the other hand, is probably a lot cleaner. But just burning it within a car engine is not so good.
Burakabe has started using a fuel cell because they are aware of that, and also the fuel cell is much more efficient. But it's too little, too late, and of course, currently the political situation in Mali is not such that big investors would like to come in and study. It's practically an inaccessible location for most purposes presently.
We are actually over time, but I wonder if I could steal 1 more minute of your time. There's a question in the chat, and I'd like to just draw attention to one part of it, which is around water usage. There are a great number of concerns around the impact of water, the impact of green hydrogen on water resources. Are there similar concerns regarding white hydrogen? I'm not sure. Professor Bambi, please come in. Picking on you because you're still spotlighted.
Yeah, I'm still spotlighted. That's okay. Yeah, I'm not sure. So that's why I sort of went quiet. The US have a feeling that the best way to exploit hydrogen resources at depth would be through stimulation. And presumably that is a similar process to fracking, which would involve the requirement for a large amount of water. So that's in contrast to what we've been envisaging in Mpumalanga, which is just to sit at the surface and wait for the hydrogen to come to us rather than any sort of stimulation at depth. So I think stimulation probably would require a large amount of water that needed to be injected for that stimulation process. If you wait at the surface, like in Burakabogo, like we envisage in Mpumalanga, then I think not.
Thanks so much. And I see Ansi, you would like to come in, and then Dr. Kramer again.
Yes, thank you. Another concern we've noticed, especially in Mpumalanga, is that the study area, especially towards the east, is an ecologically sensitive area. Again, our study focused on the natural generation of, or the geogenic generation of the hydrogen, and not the anthropogenic generation of it. As soon as you're talking about the anthropogenic one, where you would be looking at something similar to fracking, then that's a completely different question, different legislation that needs to start come into play there, and a very serious conversation that needs to be held at that point.
Dr. Kramer?
Yeah, we have looked at it a little bit, and I think by and large, it is the same situation as with conventional drilling for oil and gas. It is using a lot of water production in the drilling process itself. It is using water in the purification processes. It disrupts water flows in infrastructure and so on. So it needs to be regulated very seriously and very clearly. I don't know as of now as there is really a need for a separate hydrogen industry guidelines or so. If stimulation comes in, like there's only one example at present in Oman, then of course it is a different question. Then the whole fracking debate comes in, and in that sense, it is the same situation. Yeah. Problem is that it is not usually in the same places where oil and gas has been found in the past. So as an added introduction of elements of infrastructure into pristine areas, for example, like in Botswana.
Right. So, I mean, I think as with so many other topics, I find myself only at the beginning of a whole lot of questions rather than finding the answers to them. I mean, from what I've heard today, the question of whether white hydrogen can contribute to the energy transition not only has to do with how it was naturally produced under the surface of the earth, but also how it is being extracted and how it is being burnt. Yeah, as such, I think this has been a really fascinating discussion, but is really just the equivalent of tipping our toe in the water. And I think that it's something that we'd really like to continue exploring. Should this become and remain an important issue for the energy transition. So with that, I'd really like to thank our contributors, Professor Bambi, Dr. Smith, and Dr. Kramer. I don't know if you have any final thoughts or statements you'd like to make. If you do, please come in.
Yeah, I would like to say something. As I said in my presentation, I think it's an interesting subject. It has been completely overlooked by my profession. Geologists thought hydrogen is such a tiny molecule that it cannot be captured and is not captured. It was looked as as a nuisance by the industry, and therefore 100 years of research are missing in this case. We knew the first hydrogen boreholes from Australia 100 years ago, and they were just closed because they didn't produce natural gas. So it's an interesting case study of science not being up to speed, and now it's basically too little and too late. It is not a game changer. That is my conclusion.
Thanks for that. Professor Bambi and Dr. Smith, any other final thoughts?
Yeah, I just want to thank Dr. Kramer for that really great synopsis of the state of hydrogen exploration. I think another point that's worth saying, the very late start in hydrogen exploration has been highlighted, and it's really only in the last 5 years that the world has taken a big interest or a growing interest in natural hydrogen. So we really are in its infancy. I feel a little bit guilty talking here, saying, I don't know, over and over again. But I don't think anybody knows at the moment exactly how or what the best way to exploit this natural hydrogen could be. But there are a growing number of people working on it. Maybe we can get up to speed as quickly as possible. But yeah, it's too little, too late.
And I think from my side, I want to say thank you for the invitation and the opportunity to come and present here. And as research continues, if we'll ever get to a point where we can be on the same playing field as natural gas, the conversation needs to be open. And we are luckily in times when people have a voice and we can say, okay, but how does this affect the society as a whole? And make sure that we do it right, correctly from the start, going forward.
Yeah, absolutely. Thank you to all three of you for really, really insightful contributions. I feel far more educated than I was at the beginning of this conversation. Yeah, let me thank you again, as well as some of the people behind the scenes who made this possible. So my colleague, Elena Gnott, my colleague, Jeremy Marr, and Jörg Haas for giving life to this project behind the scenes. And with that, let me close. Thank you for all the participants who took the time to join us. I hope you find it as useful as I did. I wish you a very good evening or rest of the day. Thanks a lot.
Thank you. Bye.
Bye, everyone.
Thanks.
Thank you. Bye-bye.